Hello everyone, and welcome to the Principal Component Analysis with Python lecture. This lecture is going to be a bit of a continuation on the theory lecture, but we'll start putting in Python and scikit-learn commands into play. We'll go ahead and jump to the Jupyter Notebook in order to see how to use Python and scikit-learn to actually perform a principal component analysis, and then we'll try to give a visualization to explain what each component actually stands for. Let's go ahead and jump to a Jupyter Notebook to get started. Alright, here I am at the lecture notebook. This is under the machine learning section, principal component analysis folder. There's a notebook called principal component analysis. And since this isn't exactly a full machine learning algorithm, but instead an unsupervised learning algorithm used for component reduction, we're going to just have a lecture on this topic, not a full machine learning portfolio project. Although we will walk through a cancer set with PCA. So this is a real data set we're going to be working with. Again, make sure to watch the previous video lecture and theory presentation for a full overview of PCA. And if you want the mathematical background behind PCA, you can go ahead and do the reading from an introduction to statistical learning. But remember that overall, PCA is just a transformation of your data, and it attempts to find out what features explain the most variance in your data. So for example, if you have an original data with two components, remember we try to get rid of the components that don't explain that much of the variance in your data. So you can transform your data and then transform it back with either the second component dropped and then only have the first component here. So basically we just drop this second component and we eventually transform this to just have this information along that feature's axes. Alright, we'll go ahead and continue on. I'm going to start a new notebook using my environment to get started. Okay, the first thing I'm going to do is import some libraries here. I'm going to say import matplotlib.pyplot as plt, import pandas as pd, import numpy as np, import seaborn as sns. Let me fix the order there. And then finally matplotlib inline. Let's go ahead and walk through the data we're going to be working with. We're going to be working with a cancer data set because it has a ton of features and is a great use case for PCA. We can actually just get this data set directly from scikit-learn. So you're going to go ahead and say from sklearn.datasets import load underscore breast cancer. And you can actually just tab autocomplete that and it should work. And then what you do is you set a variable and you actually just call load breast cancer. And basically scikit-learn has this .datasets, and you can say import load, and if I just go ahead and click tab here, you'll notice that there's a bunch of options: load Boston, load diabetes, digits, etc. These are just built-in datasets that scikit-learn has in order to show some examples of machine learning algorithms in the documentation of scikit-learn. And what you do in order to use these datasets is you actually just call the load function, set it as a variable, and then that variable, you'll notice, is, if we just go ahead and check out the type of this thing, it's kind of this object type called sklearn.datasets.base.bunch. Not a typical object that we're used to working with, but it essentially just acts like a dictionary. So you can call cancer keys off of this to get the keys of the dictionary, and then you'll see that there's a description, data, feature names, target, and target name keys. And then you can go ahead and print cancer and call the description key the DESCR. If you don't call print, what will happen, just to show you, because this is kind of a common mistake with beginners, is you'll get some weird string that looks like this with a bunch of line breaks in it. So make sure to actually call print cancer description in order to see this formatted correctly. So we have 569 instances, so the data is roughly small, but it's still pretty good size. However, the number of attributes in comparison to the number of instances is actually quite large. We have 30 attributes. They're all numeric, and there's a lot of information for them. So you can check out the summary statistics here if you want all this information. But basically, this is just information on some breast cancer tumors. And what we're going to try to predict is whether they are malignant or benign. Now that would be if you're actually doing a classification on this data set. What we're going to be trying to do with principal component analysis is find what components are the most important ones that explain the most variance of this data set. We're not actually going to do a whole machine learning process on this as far as predicting what class the cancer tumor belongs in. Let me go ahead and continue to set this up using pandas. So I'm going to set this up to what we usually see for data by saying df is equal to pd.dataframe. And I'm going to grab the data key. So I have my data. Those are all just the numerical values. And then I'm going to set columns equal to cancer and then the feature names. And then if we check the head of that data frame, we get something that looks like this. This is exactly what we want. Notice we have a ton of, and in fact, there's actually a ... to signify pandas is running out of room to show them all, but we have a ton of features. We don't have the actual target. If you look at the target, so if I say cancer target, let me make sure, whoops, that's spelled wrong. Cancer target, we have ones and zeros, and if you check out the target names, it's malignant or benign. So just keep that in mind. We're not actually going to be working any machine learning algorithms off of this for prediction or classification. We're going to stick with principal component analysis. The reason being, if you were to use this data set with another classification algorithm, you would probably want to do PCA first to actually get an idea of what's important in trying to see if a tumor is malignant or benign. Okay, as we've noticed before, it's pretty difficult to visualize high-dimensional data. In this case, we have 30 dimensions. And what we can do is use PCA to find the first two principal components and visualize the data in this new two-dimensional space. Right now we're dealing with 30 dimensions, which we can't make a 30-dimensional plot here. The max we can really do is 3D, maybe 4D with some color. But what we can do is visualize this using the two principal components into 2D space. Let me go ahead and now show you the real point of this lecture, which is PCA with scikit-learn. So you're going to say from sklearn pre-processing import standard scalar. And what we're going to go ahead and do is scale our data so that each feature has a single unit variance before we actually use PCA on this. So we've seen standard scalar before. We just call it as if it was any normal estimator in scikit-learn, and then we go ahead and fit it to our data frame. In this case, data frame is just the features themselves, and then we go ahead and transform it. So we say scale data is scalar.transform df. Okay, and PCA with scikit-learn uses a very similar process to the other pre-processing functions that come with scikit-learn, such as standard scalar. What we're going to do is instantiate a PCA object, find the principal components using the fit method, and then apply the rotation and dimensionality reduction by calling transform. And we can also specify how many components we want to keep when creating the PCA object. Okay, so it's time to perform the actual PCA. We've already set everything to have standard scale. What we're going to go ahead and do is say from sklearn, and the family PCA is under is decomposition, which kind of makes sense because you're essentially decomposing this into its principal components. And then we're going to say import PCA. And then make a variable called PCA is equal to, and you actually call PCA, and you can do Shift Tab to explore the principal component analysis here. But what you're going to do is specify the number of components you want to keep. And what we're going to go ahead and do is say number of components we want to keep is just 2. And I'm going to try to visualize this entire 30-dimensional data set just by the 2 principal components. And I'm going to say n components equals 2 because I only want to keep 2 components. And then once we've done that, we go ahead and say PCA.fit to my scaled data. And then what we go ahead and do is transform this data to its first principal components. So I can say x underscore PCA is equal to PCA.transform the scaled data. And then I can check out my scaled data shape. Notice my scaled data is 569 by 30, And if I check out my XPCA shape, what I just made after the transformation, now it's 569 by 2. So I've reduced it to the first two principal components. And now that we've reduced 30 dimensions to just 2, we can actually just plot out these dimensions using matplotlib. And we can say something like this: plt.figure fig size is equal to, let's say, 8 by 6, so it's a little larger. And then I'm going to make a scatter plot of these two columns in our XPCA. So I say XPCA, these are NumPy arrays. I want to grab all the rows from column 0 and plot those against all the rows from column 1. And let's go ahead and pass in PLT X label is the first principal component, and PLT Y label, that's the second principal component. Now if I just plot this, let's make sure it runs, I now see the data plotted by the first principal component and the second principal component. And as mentioned in the lecture, interpreting these components is actually not that easy to understand. But what I want to show you is just how powerful this technique is. I'm going to go ahead and add one more argument into plt.scatter. And I'm going to say C. Remember, C is color, and we can actually pass in a column for color. I'm going to pass in the target column for color, meaning I want to color these points by malignant and benign. So I can say C equals cancer target. I run this again, and now it's in black and white. So to make this a little easier to see on your screen, I'm just going to pass in another color mapping scheme. I can go ahead and say plasma, and here we have a plot. And basically, this really shows the power of principal component analysis. Based off of just the first principal component and the second principal component, we can see we have a very clear separation of what the malignant tumors look like versus the benign tumors. And this is just based off of two principal components versus the 30 dimensions of data. Meaning you can actually almost use this as a compression algorithm of sorts. You keep a lot of the information, and we're explaining a lot of the variance still, but now we're only doing it with 2 columns of data versus 30 columns of data. Now let's go ahead and discuss what we actually mean when we say first principal component and second principal component. Unfortunately, like I mentioned, with this great power of dimensionality reduction, it comes at the cost of being able to easily understand what each of these components represent. They don't relate one-to-one to a specific feature in your data. The components really correspond to combinations of the original features. The components themselves are stored as an attribute of the PCA object. Let me go ahead and show you how you can see that. You can say PCA.components underscore, and you'll see an array of the actual components. And in this NumPy matrix array, each row represents a principal component, and each column actually relates back to the original features. And we can visualize this relationship with a heat map. So I'm going to try to show you visually what these principal components represent. I'm going to say df underscore comp is equal to pd data frame PCA components underscore, and set the columns equal to cancer feature underscore names. So here I've created a data frame. If we go ahead and take a look at it, it's a principal component 0 and principal component 1. So the first principal component and the second principal component, and their relationship for each of the 30 features. Now what we're going to go ahead and do is put this into a heat map. So we'll say SNS heat map, pass that in. I'm going to set CMap to plasma, so we can go ahead and take a look at it. And then finally, I'm going to actually make this figure a little bigger before we show it. I'm going to say fig size is equal to 12.6. And now we have a heat map that shows the relationship between the correlation of the various features and the principal component themselves. Basically, each principal component is shown here as a row, and the higher the number, or the hotter looking the color towards the yellow, it's more correlated to a specific feature in the columns. And that's really the best explanation for what these principal components represent. They're combinations of all these features. And you can see what features were specifically important to one of the principal components versus the other. All right, I hope this information is useful to you when you're dealing with high dimensional data. Now that you have these principal components, what you can go ahead and do is feed in your reduced version of these principal components. So you can feed in right here x underscore PCA into a classification algorithm. So you could do something like a logistic regression on x underscore PCA instead of doing a logistic regression on the entire data frame of features. And you can see here that this is easily separable by just almost a straight line. And support vector machines that we'll learn about later may actually be a good choice for this. Okay, feel free to post to the Q&A forums. I really recommend that you do a little extra reading for principal component analysis, such as the book Introduction to Statistical Learning topics on principal component analysis, or even just a Wikipedia page for principal component analysis. It's a really powerful tool, and it's easy just to kind of get lost in it by just memorizing a few lines of code. Scikit-learn makes it really easy to just transform data sets into its principal components, but you should really try your best to understand what's going on behind the scenes. And I think the best way to do that is through kind of creating this heat map on your own. So what I would recommend is play around with this data, see if you can see what the top 3 principal components are, maybe make a 3D analysis of that, and just really explore and play with this data so you can understand principal component analysis fully. Okay, hope you enjoyed this lecture. Thanks everyone, and I'll see you at the next one.